he needed an assistant. His longtime roommate and copyist, John Wickens, was gone. The Principia was transcribed by a new roommate and assistant, Humphrey Newton, no relation. A young student from his old grammar school in Grantham, Humphrey served him for 5 years. These two did stay friendly. In later life, Humphrey named his son Isaac in honor of his dear deceased friend. He is the only eyewitness to Newton's writing of the Principia. He reported that Newton often forgot to eat during the project. He didn't even take time to sit down. He wrote standing up, taking a spoonful now and then of gruel or milk with eggs. When he did venture outside, he would pause, as if lost, and then disappear into his chambers again. Ever-diplomatic Edmund Halley, in his capacity as clerk of the Royal Society, deserves much credit for the publication of the Principia. Halley must have been quite the flatterer. He not only persuaded Newton to write it, holding his hand all through the process, but was able to keep Newton from stopping publication because of some advance criticism from Hooke. Moreover, Halley paid for the cost of printing the Principia himself. The Royal Society was keenly interested in the book, but was nearly bankrupt and reluctant to finance it. They had been burned by poor sales of a 2-volume History of Fishes. As for Halley, all he received for footing the bills on Newton's book was 50 leftover copies of History of Fishes. So what makes the Principia such a landmark in scientific thinking? 3 laws of motion form the basis of Newton's masterpiece. They describe how objects move, the way they bounce off each other, and what happens when they are pushed or pulled by outside forces. The first is called the law of inertia. An object that isn't moving won't move unless an outside force puts it in motion. And once in motion, the object will keep on moving in a straight path unless another force changes it. The second law states that the amount of force needed to move an object is determined by the mass of the object and also the amount that its speed changes while moving. The third law, that every action has an equal and opposite reaction, is said to have occurred to Newton while observing billiard balls in play. When 2 balls collide, they bounce off in opposite directions. Another way to visualize the third law is to picture a rocket, gases from burning fuel shooting out the back to push the rocket forward. From the same principles, he wrote grandly, I now demonstrate the frame of the system of the world. His splendid unifying idea was his theory of gravitation. All matter attracts all other matter with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. What does this mean? Every particle in the universe is attracted to or exerts a tug on every other particle. For example, you as an object are pulling all the objects around you into your own gravitational field, and at the same time these objects are pulling on you. But the more massive that something is, the greater the force it will exert. An apple is much smaller than the Earth, so the Earth exerts a lot more force on the apple than vice versa. Still, when an apple falls, it actually pulls the Earth toward it a little, just not enough to be noticed. And the farther away 2 objects are, the weaker the force they exert on each other. The force gets weaker much faster than the change in distance, so if you double the distance between 2 objects, the attraction between them becomes 4 times weaker. If you triple the distance, the attraction becomes 9 times weaker. Other people had had vaguely similar ideas, but Newton was able to create an accurate mathematical equation that expressed the force. It is force equals gravity times mass of the first object times mass of the second object over distance squared. In his equation, F equals force, G equals gravity, m1 equals mass of the first object, m2 equals mass of the second object, and d equals distance. Translated, this means that the pull of any 2 objects varies inversely as the square of the distance between them. So Newton called his equation the inverse square law of attraction. Endless applications can be derived from Newton's work. He could apply his laws to orbiting bodies, projectiles, pendulums, and free fall near the Earth. This one principle explains why an apple falls to the ground, and why the moon stays in its orbit around the Earth, and why the tides ebb and flow, why the planets move as they do, and why humans don't fly into space as the Earth rotates.